Hello everybody, my name is Wolfgang Maass. I present a paper that I've written together with Lukyanenko and Veda Storey. The topic is From Mental Models to Machine Learning Models. Machine learning is more and more used for supporting decision making, and the idea of machine learning is that you learn from data by the help of training models and using that in order to make predictions. And these predictions shall support decision making in order to create values. In this talk, I'm going to focus here on the dashed area alone. So machine learning is the idea that you compress large amounts of data with the help of different kinds of machine learning models in order to derive predictions. The problem is that the data as such, if it is flat, it has no semantics, only very basic semantics. And usually the data scientists have little knowledge about the domain. So they use the data as is, and what they usually refer to is that they say they want to see what the data is telling them. And telling them means that they look into correlations and they look into patterns and to see whether it has certain kind of relation with output. The idea of this paper is to introduce conceptual models in order to inform data scientists about the meaning of data, the underlying human knowledge that is referring to this kind of data. So it qualifies the data and gives a help for the data scientist to interpret the data properly. So this, with the help of conceptual models, allows the data scientists to get a deeper understanding of the tasks and on the abstractions behind the data. When you look at the task in general, then we see the mental models, which is the internal representations and their understanding of a data scientist of the environment, and using that kind of knowledge in order to deal with the data as is, and then train a model. While the internal representation of a data scientist is a mental representation of reality, it is related to intuitions and so on, so it captures a certain kind of representation of the real world. When you talk about complex domains, these mental model representations might be insufficient. So this is the reason why we think that conceptual models could provide a shared understanding of the real world that is explicitly represented, and using that in order to deal with the task of training models. Therefore, we present an end-to-end framework from mental models to AI models with the help of conceptual models. And this is what you see here on this slide. The data scientist generates a mental model, which is an abstraction of entities and events in the application domain. And this representation is not simply used as a qualitative understanding of a domain, but used for creating explicit conceptualization of the domain in order to create a shared understanding in the data science team. On the physical world side, the data that is created from this domain is also an abstraction of this particular domain, and the data representations are input as raw data for the AI models. But now what we are arguing for is that no AI model is developed without a proper conceptual model. And the same holds for the data side, that we argue that no data shall be used in AI models without being related to a conceptual model. So in essence, what you can say is no AI model without conceptual models. We have developed and sketched in the paper a citizen science project as an example for our approach. Imagine that you want to investigate why birds die in certain areas. You find them, and as background on the mental representation, you might be informed about what plants and animals are about, and that is informed by some theory on animal behavior. Maybe also you have some mental representations about human infrastructures, what properties there are, whether there are geo-coordinates, height and width, and streets and people and cities and so on and so forth. Introducing a conceptual model, making that explicit, what is in the internal representation of your mental model as a data scientist, but to actually explicate that, write that down, gives an opportunity to scrutinize your kind of knowledge, find gaps that you might experience, and find biases because you might think that birds don't get electrocuted. That means they die when they sit on some electricity power lanes. But it also helps to integrate knowledge if you make that explicit and you can discuss it with your team, and then you find probably new viewpoints on the problem that you try to investigate. So what do we mean by that? You see here a geomapping of the red dots, and the red dots are examples for dead birds. And you see that in certain areas, and if you take a regular, let's say, convolutional neural network and you do some analytics on that, you might infer that higher altitudes are dangerous for birds. Then you go back to your conceptual model and you discuss with experts, and they say, okay, you have to look also at roads. And then you look into roads and you realize, okay, 2 of these sites are close to roads. And then you realize that this blue road is a bicycle lane. You might infer that bicycle lanes are dangerous for birds. And then you go back to your conceptual model and fill in more gaps and bring in more reasoning behind that, whether these spurious relations might actually be true. And then you realize that if you look into power lines that go cross-country, that you realize that the red dots are related and highly correlated with the power lines going cross-country. So this is an example where, depending on what your conceptual model is, you end up with different kind of solutions and predictions and values for your decision making. Okay, so this is a sketch of the framework that we presented in our paper, and we hope this steers up some discussion. With having that said, thank you very much for your attention.